Hello everyone, welcome to the session number 6 in linear algebra, which is part 1 from the postgraduate course of deep learning and applications. We have already seen in session 5 the singular value decomposition, the structure of singular value decomposition, and what we are going to explain today some more details about the singular value decomposition and how we can define the main 4 spaces of matrices as an outcome of this eigen decomposition, or the breaking down the matrix into these 3 matrices. Okay, now let us continue. Yes, so we said that any matrix A, for in general, that it is M by N dimensions. It could be like broken down into 3 submatrices, as we said we call this as U. Okay, and times D is diagonal matrix, and V transpose. And we said that this U and V are orthonormal or orthogonal matrices, which means that U inverse is the same as the transpose of U, and also V inverse is the same as the transpose of V. And since the original matrix A is M by N, so this U matrix is M by M, and V matrix or D matrix is M by N, and V matrix is N by N. So this is the dimensions of those matrices. Okay, and also we can see that this diagonal matrix or matrix consists of just diagonal elements, and the rank of matrix A is the non-zero elements of this diagonal matrix. Okay, and actually we can represent the matrix D, this diagonal matrix, as in this shape. So we have like all zeros, and we have here, maybe we can call it like diagonal but non-zero elements. So this is the non-zero elements of this diagonal matrix, and the others are 0. I will give some numerical example about this one. And also we mentioned in the previous session that the elements of the diagonal is the square or the square root of the eigenvalues of the A times A transpose, and this what time or of the singular values of matrix A, which is actually the square of the eigenvalues of A times A transpose. And this what we are going maybe to explain a little bit more here before we go to talk about the 4 subspaces of any matrix A. Remember, we don't have eigenvalue of non-square matrix, because this matrix is in general is M by N. When M does not equal to M, then there is no eigen value. The eigenvalues is not defined, but we define singular values. And now let us do something easy. So if we multiply A by A transpose, so this A is M by N, this transpose is N by M, so the resultant matrix will be M by M. Okay, now if you multiply these together, so A is U times D times V transpose times A transpose. So as we show before, that when you have like A times B, if you take the transpose of all of them, then you make B transpose times A, and we apply it here. So we will have here V times D transpose, but because D is diagonal, actually the diagonal, the transpose is the same as it is because we have only the diagonal elements. Okay, times U transpose. This will be A transpose, and this will be A. Okay, now if you make this multiplication, you will have U D, and as we said, those are orthogonal matrices, which means that the transpose of the matrix is the same as it is inverse. And this means that V transpose times V is the identity matrix, and then it will be just, it will not have any effect on the multiplication, and then we will have D multiplied by D. Now remember that this one is I, the identity, so it becomes like D times D is D inverse, okay, times U transpose. Okay, so this is important to remember about this one. Now U transpose is U inverse. It is the same actually, so it will be like U times D square times U inverse. Okay, now the diagonal square, we explained this before. If you have, let's say, 2 0 0 4, if you take the square, simply you square only the diagonal elements, so it becomes like 4 0 0 16. That's all, which means that D square is the square of the diagonal element. Okay, now look to this form. This is the A times A transpose. Okay, if you go back to session 3, when we talk about the eigen decomposition of any matrix, any square matrix A, we said that I will not make it A here because we have already A, so let us say B. So for any square matrix B, for example M by M, we said that it can be eigen decomposed, or by making the decomposition like we said X, if you remember, times Z times X inverse, and we said this called the eigen value or the eigen decomposition of any square matrix B, and we said here that this Z is a diagonal element and it contains only the eigen values of matrix P, and we said that X is the eigenvectors of matrix P, and every column here is the eigen a vector associated with the certain eigen value in this diagonal element. So we explained this before, okay, but now compare this one with this one. So actually they are the same, they are similar structure, okay, which means that U is a matrix consists of where the columns of this matrix is the eigenvectors of this A times A transpose, and of course this is the inverse of U, it is like this one, and also now D square is the eigenvalues of A times A transpose. So the diagonal elements here in this D square is the eigenvalues of what? Of A times A transpose. But what we have here, we have only D. The diagonal in D is called the singular values, and the singular values is nothing but the square root of the eigen values, the square root of the eigen values of A times A transpose, because there is no eigenvalue for non-square matrix, but we have singular values in this case. Okay, and now we if we make the reverse, if we multiply A transpose times A, so A transpose means is that it is N by M, and A is M by N, so the result will be N by N matrix. And do it the same here, so what we get is this one, so it becomes like V D then U transpose, okay, times U times D times V transpose. The same, so we have here U times U transpose is the identity matrix, because as we said, U is orthonormal matrix or orthogonal matrix. Then we will have here V times D square times V transpose. Okay, and again here we have V is the eigen consists of all the columns of V are the eigenvectors of A transpose times A, and D square is the contains the eigenvalues of A transpose times A, and V transpose, of course, is the inverse of V, so it can be also V minus 1. So this is the reason that when we talk about singular value decomposition, when we say that U is the contains the eigenvectors of A times A transpose, and V the eigenvectors of A transpose times A. Okay. As we mentioned also in the previous session, we usually we can call this U as the left eigen vectors, or and this V is the right one, because it comes to the right direction. Okay, now we want to see like in more details about this factorization of matrix A, how it could add some information, or how can we see more about the internal structure of matrix A. Okay, remember that this matrix A, as we also mentioned, that it can contain like or represent some data, as we said in the beginning, that if we have just table where we have people here, for example, so we have person like 1 and person 2 and so on, so and then we have some like attributes or features like the weight, or a blood pressure, for example, maybe the if the person is diabetic or not. Maybe we can actually add any more information that we have from the like from database in certain health center, and now we want to analyze this data, because now we can represent this data as a matrix A, and this matrix A consists of, for example, M times N, and M is the number of people and N is the number of attributes. Usually M does not equal to N. Usually it can be rarely that M equal to N, and then in this case we want to analyze this data. In order to be able to analyze this data, we need to understand first what this UDV means physically, because what we have seen now mathematically how it will be computed, but how this could describe the internal structure of the matrix A. Okay, many times in many areas we call this as the Eigen structure of matrix. Eigen structure of matrix. This breaking down of a matrix into those three sub matrices is called the Eigen structure of the matrix, which contains great information about the data in matrix A. Okay, let me go to another slide. Okay, so now the matrix A, sorry, yeah, now the matrix A, for some reason, matrix A, as we said, it could be represented as which is in general N or M by N. As we said, it can be represented like U times D times V transpose, where D is diagonal matrix, and U and V, we explained them already. This one, it could be also described as A equal to, it is the same, we can actually divide this U matrix like into two parts. We can call it like the columns, the first columns to the left side, we call that UL, and also we have the columns to the right side, we call it UR. Okay, and this D matrix, as we said, it is 0 everywhere, except the diagonal. So it is 0 here, 0 here, but actually not all the diagonal exist, okay, because m is not equal to n, and actually the singular values are non-zero only for the independent rows or independent columns of the matrix A, and this must be less than or equal to the minimum of m and n. For example, if you have a matrix with, let's say, with maybe 10 rows times 3 columns, okay, so the number of non-zero elements in the diagonal must be less than or equal to 3. It will never be more than 3, because the rank of this matrix A is less than or equal to 3, okay, is the independent number of columns or rows, okay. And since it is possible also that we have some linearly dependence between even those three columns, then the number of the rank can be less than 3, okay, but can never be more than 3. So that we divide this into two parts. We call this like the diagonal for, I will put here non-zero in the diagonal element. So some books you can find they use this z, some books, but okay, you can use any symbol, and then we have the others are 0, okay, and then it will be multiplied by the v transpose. It can be also represented like this one, so without the transpose, because if we want to keep the transpose, we should have this like v up and v down, transpose and transpose. We can be up and down, but then I can also make it like in the same shape as this one, so it will be like v left and v right, which means that we take the transpose of the original v here. We take the transpose of original v, and then we can we can represent it in this way, okay. Yes. Now by looking to this representation, you can see here that looking to this structure, we can solve this A like into, or we can define actually 4 subspaces. I will not go in details about this because it is more like details related to linear algebra, but I am interested to what we need in this deep learning analysis. So looking to this A, we can define the column space of A. What is the column space of A? Usually we call it like C of A. C of A is the column space of A, okay? And if you go back to session 1 or session 2, I described them when we talk about column space and row space. So the column space of A actually is nothing but the column space of UL. It is the same as the column space of UL, which means that the columns or the basis of A is the column vectors in this UL. Okay, and UL, what is the dimension of UL? Of course, the number of rows in UL is m. It is like this one, but not n, because all this is n, the number of columns. So we take the number of n, which are equivalent to non-zero elements in the diagonal matrix. For example, if we have here, okay, of course I will give numerical example, but just to explain this in fast way. So if we said that, as we said that this is 10 by 3, okay, and then assume that the rank is 2 of this matrix, okay. So what it means that UL is 10. We have 10 rows, but here we have 3 vectors because it is 10 by 3, so we have 3 vectors here, okay. So but because this is 10, okay, so now I mean this is the 3 possible of vectors that can be independent, independent. However, because we have only 2 independent, vectors, then this UL, it will the number of columns here, it will be only 2 vectors, Okay, and what about the other 8? The other 8 will be here. It is called UR. And why we take this 2 UL? Because actually only we will have 2 singular values here which are not non-zero. All the others will be 0. All the others will be 0. We have only 2 non-zero elements here, because this matrix will be 2 by 2. This matrix, non-zero matrix, will be 2 by 2. As I said, we will see a numerical example about that. Okay, and of course this will be 3 by 3 as well. So and now, because this will be only 2 as corresponding to this 2 by 2, so it will be 2 by 3 here, and we have 1 by 3 in the other vector. Okay, so the column space of A is the same as the column space of UL. This is UL. Okay, and what is and now we define a new term. We define the term of null space of A. What is the null space of A? The null space of A is the space where, when we project it in any vector, it will be projected to 0. It will be projected to 0. So the null space of A is equal to the column space of UR. This is called the null space. Null space. Null space of A. For example, if we okay, I will come to this with numerical things, but it means that when you multiply, if we want to multiply, this is A times any vector x, okay, and A is m by n, and x is n by 1. So actually the result that we receive is by projection of x in the column space of A. In the column space of A, but in the null space of A, the projection of x will be 0. The projection of x will be 0, and the null space and the column space, both of them, they are orthogonal to each other. They are orthogonal to each other. This we can see later. Okay, and now if you go back when we talk about column space and row space, actually the row space of A, is the same as the column space. Is the column space of VL. Okay, and the null space of A transpose, is the same as the column space of V right. Okay, now this is actually the general concept. Before I continue, I want just to I forgot to mention one thing, that in general box, when it is possible to have complex numbers, instead of t they put h, which means that it is the Hermitian transpose, because this v it might contain complex number, and when it contains complex number, when you make the transpose, you take the conjugate of each number. This is the reason that some books they write here h, if when you are reading, you yeah, so as I said that so in some books, if you read from some books and you found that they use h here, it means that v or the elements of u and v can be also complex numbers, and when you take the transpose, you take also the conjugate of that complex numbers. But here we talk about with the real numbers, and we deal with the real numbers, so it is enough to write the transpose in this part. Okay, so those are called the four main spaces of any matrix A: the column space, the null space of matrix A, and the row space, and the null of the A transpose, or the null of the row space of matrix A. And those are very, very important. We can see here, actually, if we multiply A times X, it is equivalent to the multiplication of UL, and here UR, and here we have zeros except this D non-zero, times VL, and we have here VR times X. Okay, now if you look to this one, it will be actually here will be zeros, all of them will be zeros, and zeros times VR, it will be zeros, and we have only non-zero in the dnz times VL times x. This will be the only non-zero part here, but still we can represent this because this will be just a vector, and we can call this vector like u, like y, for example. And because also the multiplication of ur here will be zero everywhere except for ul, so actually this will be equivalent to ul times y. Okay, ul times y. This is y, and then it will be zeros except ul, and this ax will be ul times y. Okay, and the other part, so it is enough actually to take ul times y is function in x. This represents the multiplication. The others are is the null space ur. If you take ur, then the result will be zero. Because this y will be projected in the zero to the null space, which is the result will be zero there. So this is the 4 main spaces of any vector A. Okay, now let me take a numerical example to explain those concepts here. Okay. Actually, I have used Octave to make some example. So I just generate this matrix A. I assume this matrix A, very simple matrix, the simplest one that you can think about. This is a natural flow of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the matrix that I assumed here. Okay. And then I use in Octave, I use this function u d v, okay, equal to singular value decomposition of A, and then it generates numbers, like it gives me the u, the left eigen vectors side. It gives me this. It is a little bit long, but it will be, because now what we have 4 times 3. Of course, this u will be 4 by 4, and it gives me like minus 0.14, 0.8, 0.54, minus 0.04, and so on. So I will not write all of them, but just to take this concept, 0.37, and so on. So it is 4 by 4. And also it gave me the diagonal element. So it the diagonal matrix, it gives it like this way. So D equal to, you can see here is this 4 by 4. So D should be 4 by 3. 4 by 3. And actually the numbers, let me just put it on the Octave, yes. So the numbers, it was 254, okay, and 0, 0, and then 0, then it gave 1.3, okay, and 0, and then it gave 0, 0. This number actually is 10 to the power minus 15, which is due to the numerical errors or noise. So we can put also 0, and then finally 0, 0, 0, because the last 0 must be 0, because of the as we said, it is 4 by 3, so the rank will be less than or equal to 3. So this is the maximum rank, it can be 3. However, because there is dependency in this matrix, you can you see where is the dependency here? Can you see where is the dependency between two vectors in this? So you actually, I will leave it for you. So if you just a little bit concentrate here, you will see the dependency. Where is the dependency in this matrix? Okay, so and now this was not absolute 0, when we make the computation with the octave, it gives me like 10 of the power minus 15, and this is due to the numerical errors actually, because it is 0 already, so you can take it as 0. Okay, now if you look to this structure of this diagonal matrix, actually it can be seen as this, as we saw. So now this is the diagonal, which is non-zero, and here all the others are 0, and the projection in 0 will be 0. Okay, and finally we have the V matrix, which is 3 by 3, the orthonormal matrix, and it was given like I think it was minus point, it was of course V transpose, this one minus 0.5 and minus 0.76, and so on, and here we have minus 0.4 something. So now we have 3 by 3 matrix. Okay, if we look to this structure, or this decomposition of this matrix A, okay, and you can see here that the first eigen vector here, this is the column, the first column is the first eigenvector in U, and here we have the second eigenvector, and so on. So now since we have 2 by 2, then actually U to the left, which is the column space of matrix A, could be represented as, this is the column space, it could be represented as U1 and U2. Actually, you can take it from here. This is the first column and the second column. So it will be like U1 is, if I just check it on the octave, yes, so it was like minus 0.14, and here we have minus 0.34, here we have minus 0.54, and here we have minus 0.75. This is the first eigenvector, and the second eigenvector is 0.82, 0.42, 0.02, and minus 0.37. This is the column space. This is the column space of matrix A. Okay, and of course in this V, the first two, it will be the row space, Okay, now let me check in this one. Okay, if I asked you question, what is the most important component in this matrix? Actually, you can see those matrix U and V, they are orthonormal, which means that their length is equal to 1. Okay, and it is a scale is given here. Okay, so the highest, remember this, the highest information in this data is the eigen vectors associated with the highest eigenvalue, or singular value. Sorry, this is not eigenvalues. If I said eigenvalues is wrong, those are singular values. Okay, so the highest singular value, it represents the maximum information content in this matrix A. So this 2.54, this is very large number, which means that the first eigenvector, it has the highest information. Okay, so we can actually find it, because we can take this U1 times 256, is just a scalar number, this is the singular value, times V1 transpose. Okay, so now this U1 is 4 by 1, multiply this is just a number, okay, and this will be 1 by 3. Okay, so the result here, we will have another matrix is 4 by 3 matrix, and this matrix represents the first component of this matrix, which contains the highest information. So the highest information can be extracted from matrix A by multiplication of the eigen vector of U associated with the highest singular value multiplied by the row vector in V. So now we have the highest information content in this matrix. Okay, what is the second highest information? Is that one was associated with the second singular value. So the second singular value is 1.3, so which means that you take U2 multiplied by 1.3 multiplied by V2 transpose, then you will get the second component. If you add them, if you add the first component, let me call it like maybe B1 plus B2, if you add them together, those first two components, actually you will generate the matrix A, but in different form. So it will be the same as matrix. It will contain all information. We just remove the null space from this matrix A, and then any number you multiply in X, it should be the same as if you multiply it in this numbers. So we have the first component and the second component, and actually this is what is we know that as the principal component analysis, which we will see them in details later in this course. So remember that this is it is very important, this singular value decomposition, because it can decompose the data or the matrix into some paths which reflect the information content in this matrix. Okay, sometimes the statistician, they call it like maximum variance, but we call it also in machine learning that maximum information. Maximum information is the part which is associated with the highest singular values. The other zeros are just null space. The other zeros, the projection of the others, which means that in this case U3 and U4 in this matrix, actually they are projecting in the null space. So if you multiply any matrix with any vector X, okay, where it can be two parts, part from the column space and part plus 0, and this 0 is the part in the null space. The part in the null space. Of course, the null space also contains some information if we want to study the noise structure or the disturbance or the noise inside the matrix A. Both of them, they are orthogonal to each other. More details about this will be seen in the application part in this course, but this is when we talk in this course about singular value decomposition, what is the conceptual meaning of singular value decomposition, these things should be clear already. Okay, my suggestion or my advice, just go to whatever computer package that you use and try to generate some matrix. Okay, any matrix that you can think. It is better that to be not non-square. By the way, that even for square matrix you can apply singular value decomposition, so it is very general. And also singular value decomposition is used to remove, as I said, that any zeros or small numbers, and this can be used when we want to inverse matrix, the invert matrix if we have square matrix but the condition number is large. So the condition number of matrix A is defined as the maximum of singular values of sigma the I for all I divided by minimum of I of sigma I. So we divide the maximum singular value divided by the minimum singular values, of course the magnitude. Okay, so in that case, if we have very large condition number, then this matrix is called ill-conditioned. Ill-conditioned matrix, you cannot find the inverse, or you can do it in computation, but it will have very large errors. It will have very large errors. Okay, so one way to make it well conditioned, that they make the singular value decomposition of this matrix A, then they remove the close to zero I singular values. So they cut the close to zero singular values and make the multiplication again, and then they will have like more robust version of the matrix A, which can find it is inverse without large computational error. And actually this is what is many of the ready packages they use already. When you use for example in Octave, if you use B inverse, any matrix A, they use it in this way. So if A is a square matrix, they will make it will condition. If A is non-square matrix, then it will generate A plus. That what we described it in the previous session. Okay, so what is good for you to understand what we are doing, that you generate any matrix or you suggest any matrix, and then you use singular value decomposition. Then you will have U, D, and V, for example, from as an outcome of from this singular value decomposition. Try to multiply U with U transpose to see yourself that it will be the identity matrix, which means that the transpose is already the inverse. And also try to remove the 0 or close to 0 elements from this diagonal matrix, and remultiply those numbers with this non-zero diagonal elements, and construct a new matrix, and then have any vector x, multiply x by A, and multiply x by this new generated matrix, and you will see that both of them, they will give the exact solution, even though it is a reduced version from the original matrix A. Okay, and then you can take the other part, the others, for example, hey, here U3 and U4, and here is V3, and take those and generate a new matrix, and then try to multiply them in the same vector x, and you will see that it will be projected to 0. It will be projected to 0 space. It will be null space. So it is very interesting, and it is very interesting part that you will see yourself some interesting features by doing this decomposition. Okay, and in the next in the coming session, we may go to the some maybe numerical examples, more numerical examples, and also we will see different conceptual analysis of linear algebra, which is useful in our machine learning course. Thank you very much.